Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on equilibrium expression and equilibrium constant. Last time, we discussed the differences between reversible and irreversible reactions. Reversible reactions are chemical reactions which result in an equilibrium mixture of reactants and products. Equilibrium is present when the chemical activities or concentrations of the reactants and products have no net change over time. Irreversible reactions are the opposite. They are chemical reactions that only proceed in one direction and do not result in an equilibrium mixture of reactants and products. The chemical activities or concentrations in these reactions have a net change over time. We also learned about dynamic chemical equilibrium in our last lesson. This happens when the concentration of the reactants and the products are constant with time. It is when the rate of the forward and reverse reactions is equal, and thus it only applies to reversible reactions. Today, we are going to learn about the law of mass action. We will define equilibrium constant and also write the equilibrium constant expression for chemical reactions that involve concentrations. Let us begin. The law of mass action characterizes the dynamic chemical equilibrium. Norwegian scientists CHEM Goldberg and Peter Vogt studied reversible reactions and came up with this law. It states that the combining power of two reactants, A and B, depends upon their nature as well as their active concentration. It also states that the rate at which these two reactants combine is directly proportional to the product of their concentration terms, each raised to the power of its respective coefficient in the balanced chemical equation for the reaction. This is the general equation that represents a reversible reaction. A and B are reactants. M and N are products. And A, B, M, and N are stoichiometric coefficients of the balanced chemical equations. It is assumed that the reaction is homogeneous in nature. This means that all the reactants and the products are present in the same state. The rate of forward reaction depends on the concentrations of A and B, or the reactants. This is shown in the following expression. In this expression, the square brackets A and B are concentrations of the reactants, respectively. The rate of reverse reaction is given by the expression in square brackets. M and N are the concentrations of the products, respectively. K subscript F and K subscript B are rate constants for forward and reverse reactions, respectively. At equilibrium, the rate of forward reaction is equal to the rate of reverse reaction. Kf and Kb are constant. Therefore, the ratio of Kf to Kb is also a constant. The ratio of Kf and Kb is represented by K subscript Eq. Since the constant represents the reaction at equilibrium, it is known as equilibrium constant. The square brackets M, N, A, and B, or the products and the reactants, are concentrations at equilibrium. When the concentrations are expressed in molarities, which is the measure of the concentration of any chemical species, the equilibrium constant is represented by K subscript C. When the reactants and the products are in the gaseous state, their concentrations can be expressed in terms of partial pressures. In such cases, the equilibrium constant is denoted by K subscript P. This is the expression of equilibrium constant in terms of molarities for Kc and Kp, and interims of partial pressures for Kp. Students, let us do an activity. In a moment, you will see a reaction. Write the equilibrium constant expression, Kc, for the following reaction.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. Were you able to write the equilibrium constant expression for the reaction shown? Your answer should look like this. Please take a moment to check and make sure yours is correct. Let us now discuss an experiment that determines the equilibrium constant for an organic acid. We begin by taking a 100 milliliter round bottom flask and adding 10 milliliters of 0.5 acetic acid and 10 milliliters of 0.5 propan 1-ol. Add 5 drops of concentrated sulfuric acid to the solution, along with a few pieces of boiling chips. Then, attach a water condenser and reflux for 1 hour on a water bath, as shown here. After, cool the flask and its contents in an ice bath. Pipette out 1 milliliter of the reaction mixture in a conical flask containing 25 milliliters of ice-cold water. Add 2 drops of phenolphthalein indicator to the solution in a conical flask. Titrate the contents against 0.1 m of sodium hydroxide. Repeat these 3 steps 3 times and take the average volume of sodium hydroxide consumed in titration. The esterification of acetic acid is represented by this equation. Assuming the total volume of the solution is 20 milliliters at the end of the experiment, the concentration of the individual species at equilibrium can be calculated like this. The equilibrium constant for the esterification reaction is calculated like this. Students, let us do another activity while all of this information is fresh in our minds. In a moment, you will see a table. Please match each term on the left side of the table with the description that best matches it on the right side of the table.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. The law of mass action expresses the relative concentration of reactants and products at equilibrium in terms of an equilibrium constant. Equilibrium constant is used to determine whether a reaction has reached equilibrium. Dynamic chemical equilibrium is when the rate of the forward and reverse reactions is equal. Let us continue. In today's lesson, we discussed the law of mass action, which characterizes the dynamic chemical equilibrium. We also defined equilibrium constant as a way to determine whether a reaction has reached equilibrium. We finished our lesson by writing the equilibrium constant expression for a chemical reaction that involves concentration. This brings us to the end of our lesson for today. Until next time, thank you, teacher. Thank you, students.